My name is Christoph Skupin. I am an FPGA and software developer at Swabian Instruments. Today I will show you how we at Swabian Instruments use the Red Pitaya hardware to build a pulse generator for scientific use cases, the Swabian Instruments Pulse Streamer A2. What exactly is the Pulse Streamer A2? The Pulse Streamer A2 is a digital pattern and arbitrary waveform generator with 8 digital and 2 analog output channels, which are always synchronous. The device allows you to output precisely timed complex pulse sequences and waveforms efficiently. The digital channels offers a 1 nanosecond timing resolution with output voltage levels of 0 and 2.6 volt. The analog channels provide an output voltage range of ±1 volt with a 14-bit vertical and an 8 nanosecond timing resolution. All outputs are designed to drive 50 ohm loads, as is common in high-frequency applications. With the pulse streamer, you can use software trigger or you can apply external signals for the trigger and clock. The corresponding input ports are on the pulse streamer's left side. The device communication interface is a 1 gigabit per second Ethernet, and its 512 megabyte internal memory allows you to set up sequences with 1 million pulses. How do you communicate with the pulse streamer? You can talk to the pulse streamer via Ethernet, so you can set it up anywhere in the lab and use it from anywhere. No driver installation is needed, and for controlling the device, you can use our graphical user interface or your favorite programming language as long as it is one of Python, MATLAB, or LabVIEW. The communication is performed over the network via remote procedure calls. The RPC calls use JSON RPC, Google RPC, and one proprietary binary protocol as encapsulated protocols. Our customers particularly appreciate that Pulse Streamer allows convenient and intuitive handling and programming so that you can fully focus on your application. So what are examples of these applications? The Swabian Instruments Pulse Streamer A2 is applied worldwide in demanding scientific use cases. The scientific community and industrial research use the device to control their experimental setups. The application field ranges from quantum computer research and other applications in quantum physics to geodesy applications. For example, our partner Orca Computing in the UK uses our Pulse Streamer A2 in their devices built for the research in quantum computing. The Toyota Research Institute in Japan and IBM Switzerland make use of it with optically detected magnetic resonance, and the German Aerospace Center DLR in Stuttgart, Germany uses our device for the satellite radar ranging. So what is the pulse streamer composed of? To answer this question, let's take a look at the inside view of the Pulse Streamer A2. As you can see, the Red Pitaya stem lab is in the heart of the device. It is attached to a proprietary printed circuit board. This PCB is responsible for the power supply, the external trigger and clock input circuits, the output enabling, and it holds the digital output drivers. The housing provides port labeling and openings for status LEDs, Ethernet cable, and the 12-volt 1.5 amps power supply connection. Now let's focus on the components of the Red Pitaya board itself. The core of the Red Pitaya StemLab 12514 is the Xilinx Sync, which combines a CPU and an FPGA as system-on-a-chip architecture. Overall, we use the following components of the Red Pitaya board. First, the CPU of the Sync 7000 runs a customized Linux operating system with proprietary Pulse Streamer software. Second, we use the micro SD card interface. The SD card holds the complete firmware and user configuration data. For communication, as mentioned, we use the Gigabit Ethernet interface. Furthermore, The EEPROM connected via I2C is in use for storing the license key of our devices. The license is checked via RSA encryption at boot time. The DDR3 SDRAM works as the main memory for the CPU and stores the sequence data in a protected area which the FPGA reads out. Of course, we use the FPGA of the sync, which processes the sequence data and applies the control and data signals to the output stages. In addition, we use the Xilinx analog mixed signal module of the sync to monitor the onboard temperature and the power supply state for diagnostics. Before we come to the detailed development examples, let's look at the simplified schematic of the FPGA internal design for a better understanding. It shows the data path inside the FPGA and a small part of its internal control signals. We access the memory controller from the FPGA side via two high-performance ports of the memory interconnect. With two data mover modules, which access the memory map data and provide streamed data at their outputs, we fill two FIFOs, whereas both data movers fetch one memory block in turns. The data decoder module brings this data in the correct order and decodes it to the internal data format. After crossing the boundary of the output clock domain, a decoder module performs run-length encoding and applies data and control signals to the digital and analog output stages. With that basic knowledge about the internal structure of our pulse streamer, we can discuss two exemplary development issues we faced. The first example is connected to the data rate through the high-performance ports, and the second concerns the data and control signals of the analog output stage. To understand the direct link between the data rate through the high-performance ports and the memory bottleneck issue, we have to come back to the representation of the sequence data of the pulse streamer A2. The high-level description of sequence data can be seen as an array of a structure composed of a 32-bit integer value for the duration, an 8-bit mask for the digital channels, if a bit set, the corresponding channel is high, and two 16-bit values for the analog channels. This structure is derived from the individual signal patterns by merging all patterns into a sequence object consisting of an array of sequence steps, each defining a constant level for a specific duration for all digital and analog channels. On the contrary to the high-level description, at the output stage in the FPGA, the low-level sequence data is represented as a stream of 128-bit data words. They consist of a 32-bit count value for run-length encoding, 8 by 8-bit chunks forming a 64-bit matrix for the digital channels, one chunk for every channel, and two 16-bit for the analog outputs. To preserve synchronicity between the digital and analog outputs, the base clock of the output stage is running with the 125 MHz sample rate of the digital analog converter. So every 8 nanoseconds, a 14-bit value and an 8-bit chunk are fed to each analog respective digital channel. The maximum data rate at the memory ports appears if any output changes every 8 nanoseconds. This leads to a data rate of 16 gigabit per second. On the other hand, the memory itself works with an external frequency of 1066 MHz, transferring 16-bit per clock cycle, which results in round about 17 gigabit per second. So the maximum data rate is already close to that limit, but the CPU also needs the memory, and the memory itself needs some operating time for internal operations. So the maximum data rate at the high performance ports of the RAM will lead to, and has indeed in the past led to, an underflow issue. How did we deal with that issue from the developer side? Our first approach was to reduce the throughput of the data pass from and to the memory controller except those of the high-performance ports. Therefore, we throttled the CPU memory requests with the Advanced Quality of Service module of the Sync. It provides facilities to regulate some transaction parameters. Together with a minimal concept of data reduction, as you do not need 32-bit to represent an RLE value of 0, we got a stable, underflow-free data streaming at the cost of strongly reduced CPU and data upload performance. The concept worked with the required result, but the disadvantage of that approach was that much testing was necessary, as you can easily hang up the whole system by limiting the CPU memory access too much. Furthermore, it worked significantly on the edge, limiting us in developing new features. So we introduced a new device internal memory data format. With that approach, every data word is preceded by a header byte, which codes that data that only the differences have to be saved. In the running state, despite a lot of involved logic for multiplexing and shifting bytes, the decoder in the FPGA can output one data word per clock cycle. That leads to a new maximum data rate of 13 gigabit per second, but only if every, so not any, channel is changing. With shifting the whole address calculation for memory access from the CPU side to the FPGA, which wiped out vast data traffic between CPU and FPGA, we no longer need CPU memory request throttling even in the unrealistic theoretical maximum data rate situation. As the second development example, I want to show you an issue with controlling the digital analog converter of the Red Pitaya STEMLab 12514. The DUC is run in interleaved timing mode. With the interleaved mode, the select signal IQ cell addresses the analog channel to be updated according to whether it is high or low. As you can see, the interleaved data is presented on one data line and changes with a double data rate respective to IQ cell. The clock and the write enabled signals of the digital analog converter are also running with the double base clock. Therefore, both analog channels are updated in one base clock cycle. During measurements while implementing the feature to calibrate the pulse streamer's analog outputs, we detected unwanted noise on the analog outputs. Furthermore, we realized that the output range into 50 ohm load sometimes did not reach the full ±1 volt. As we already also planned a new version of our proprietary PCB and housing of the pulse streamer A2, we contacted Red Pitaya to discuss the opportunity for some improvements of the analog output stage, which resulted in a custom Red Pitaya version for Swabian Instruments, which is meanwhile available as the Red Pitaya STEMLab 12514 low noise. The modifications concerning the basic 12514 are made of an additional voltage regulator, which makes the power supply of the analog output stage independent from voltage fluctuations caused by variations in FPGA load. The Red Pitaya board had already been provided with the possibility to add this voltage regulator, so part of the noise issue had already been on the radar. In addition, the LN board has a slightly modified output stage to guarantee a voltage range larger than ±1 volt into 50 ohm, so it is precisely ±1 volt after calibration. Furthermore, we added some advanced logic to the DUC write enable signal to reduce additional noise which results from the crosstalk of the digital control and data signals of the digital analog converter. Here you can see how our solution improved final performance. The plots show the nonlinear error of the full measured analog output range. Therefore, we calculated the linear range less its linear fit. The nonlinear error is shown in the unit of the least significant bit, which is roundabout 122 microvolt. As you can see, the basic board without advanced control logic shows a maximum deviation of +5 minus 12 by LSB, whereas the nonlinear error decreases to plus minus 2 by LSB with our modification in the control logic and by using the Red Pitaya StemLab low noise. Finally, I want to give a short presentation of Swabian Instruments. We are a test and measurement company headquartered in Stuttgart, Germany. The company was founded in 2016 and, since then, has evolved to one of the global single-photon quantum technology leaders. The name comes from the word Swabia, which means a cultural, historic, and linguistic region in southwestern Germany where we are located. Swabian Instruments offers modern FPGA-based digital data acquisition and signal generation systems. We produce streaming time-to-digital converters, our Timetagger, pulse generators, our pulse streamer, synchronizers for our Timetaggers, and now we are at the last stage of developing an innovative dynamic light scattering device for measuring the sizes of nanoparticles and polymers. We are always looking for new engineering talents from all over the world. So if you want to join our fast developing international team, then do not hesitate and visit our career page. And finally, thank you for your attention. I really hope that my talk gave you some idea about Pulse Streamer and how we achieved such results with the help of the Swiss Army knife for engineers, Red Pitaya.